Everybody, happy Monday. A student asked me to upload all the videos for the lessons starting on Sunday, so hopefully that will be my new goal. We do have full lessons around quadratic this week. I'm giving you 2 days for this first lesson, then 2 days for the next lesson, and then 1 day for the last lesson because it's kind of shorter. We're going to continue our study of quadratics. Right, so repeat after me, quadratics. Forget the objective up there. I don't even know why that objective's there. I must not have changed it. Okay, we'll talk more about what our goal is today, but we're still studying quadratics. You saw that it represents roller coasters, right? We feel like go up and back down, and we notice some key features, and we're just going to kind of quickly summarize those key features. And kind of give some of those key features, some of those things you might have, some of those features you saw about a quadratic function, some of that uniqueness, and we're going to give names to it. So this is Arduino, so pause it now, but I'd want you to write an equation for each line. I did include the handout there so you could try it. Okay, well, I'm going to go over it now. So if you don't want spoiler, we're going to do this. Ready? So, wow, that's weird. Okay, so I'll put both answers up. So if you remember, writing equations for line normally are in the form y equals mx plus b, where we have our slope and we have our y-intercept. That's back in chapter 4 as well. But there are these two non-slanted lines. We have a horizontal line, like an A, which has a, well, if you found the slope and rise and run, you'd find it has a slope of 0, but it does have a y-intercept right here. So this could have been written as y equals 0, x minus 4. But mathematicians get rid of that 0x, so it's just y equals negative 4. Now, most students forget how to do these vertical lines. Right? What we did talk about was that this is actually not a linear function. It can't be written in the form y equals mx plus b. It has no y-intercept and has an undefined slope. So it can't be written in y equals mx plus b. So what we had discovered is that it's actually written in the form x equals something, whatever all the points go through. And if you look really closely here, you can see that for every point on this line, the x coordinate will be 3. Like this is 3, 0, this is 3, 1, this is 3, 2, this is 3, 3, this is 3, 4, this is 3, 5, right? 3, negative 1. So vertical lines come in the equation form of x equals 3. All I have to do is find out where it goes through the x-axis. Kind of easy, right? It's easy to forget too, but it's super easy. All right, so I have another one for you there. So take a look at this one. Can you write an equation for this line? Well, it's vertical. Pause it. Pause me. Don't keep listening to me. Pause me. Okay, hopefully you pause me and you're back. So we just look at it. It has no y-intercept. It has an undefined slope. But we do see that it goes through the x-coordinate, negative 1. So that's the equation. I know, super simple. What? Yes, that is the equation for vertical lines. They always come in the form x equals. Oops, sorry. Okay, and this is going to be important. We're going to talk about this more, but this line, this line is x equals negative 1. Vertical lines are always x equals whatever they go through. Okay. So, again, forget that objective. Don't even look at those objectives. We're going to summarize some of the key features of a quadratic. Okay. So, I think there's a handout that I included, which already has the names of the key features. I'm just going to go over them with you. And looking forward, we actually have to be able to find the key features of a quadratic. So, this is a quadratic functions graph. It looks like this, kind of like our roller coaster. It's not the same graph as our roller coaster, but it looks similar. So, key features. Here's a new word. You might see it on your paper. The shape of a quadratic function is not a straight line. We don't call it a hill or a frown. We actually call it a parabola. So, repeat after me, parabola. This is what we do in class. Parabola. Parabola. Not parabola, which some students say, but it's called a parabola. Mathematicians, you could look it up, come up with a name, but this shape, the shape of a quadratic functions graph, is a parabola. This shape you see like a hill. The definition is there. It's a U-shaped curve with certain specific properties, which always has a quadratic equation that goes with it. We noticed that it was symmetrical, right? So when things are symmetrical, they have something called a line of symmetry. All quadratic functions have that line that's symmetrical, and we call it the axis of symmetry. So repeat after me, axis of symmetry. Nailed it, one more time. Axis of symmetry. All right, just Daniel, go. Just kidding. Okay, so axis of symmetry, it's a line that passes through a figure in such a way that part of the figure on one side of the line is a mirror reflection of the part on the other side of the line, like it's a mirror image, which I know you might have studied in 6th and 7th grade. Okay, other key features. We noticed that there's a high point, right? The maximum point on a graph, both in the perimeter problem and the roller coaster. We call that the vertex. So repeat after me, vertex, vertex. All right, try it again, vertex. Cool. So we have quadratics have vertexes. It's the point where the parabola crosses its axis of symmetry. Right, so that's a really important one. This can be either minimum or maximum, which we're going to talk about for now. But for now, we have a maximum vertex. And take a look. It goes through the axis of symmetry. Kind of an important point. It's right there, right in the middle. Splits it in half, and it goes right through the axis of symmetry. Axis of symmetry goes through it even. I don't know. Okay. Quadratic functions can have Y-intercepts. There it is over there. We know the Y-intercept. It's the coordinate of the point where a line or curve crosses the y-axis. In this case, it's the curve, right? And another key feature is that quadratics functions can have X-intercepts. It's the coordinate of the points where the line or the curve crosses the x-axis, right? Okay, we could go do that for our roller coaster, but we're not going to do that today, okay? So we've got those key features. So what I would love you to do is open up to this page. I know graphing might be hard if you can't print it out, but you could just make a table. So like, take a moment. A ball is thrown in the air. The path of the ball is represented by the equation h of x equals negative t squared plus 8t. I want you to make a graph over the intervals 0, which is less than or equal to t, which is less than or equal to 8, on the graph below. Make sure to label the axes and all the key features. So remember, if you remember this interval notation right here, right? We talked about it in chapter 2, maybe, inequalities. It's just saying, another way of saying from 0 to 8, right? All the numbers from 0 to 8. So we want to plug in all the t values from 0 to 8 into this function and see what we get. So whoop, boop, boop, boop. So I have it here. Kind of a really important point. So here is the graph. I took the 0, plugged it in for t. So I have negative 0 squared plus 8 times 0. And that's 0. You put 1 in. Careful here. See how that negative sign is outside? It gets a little tricky. That negative sign, what you have to do is actually square the time first and then make it negative. So it would be 1 squared is 1, and then you make it negative 1 plus 8 times 1. Same here. You do 2 squared, which is 4. Then you make it negative, because we do exponents before this negative out here, right? Then 8 times 2. Then you do 3 squared, which is 9, and then make it -9. You do 4 squared down here, which is 16. Then you make it -16 before you do anything else. Then you do 5 squared, which is 25, and then make it negative. 6 squared, 36, then make it negative. 7 squared, 49, then make it negative. 8 squared, 64, then make it negative. Okay? In all those cases, you're going to do 8 times 1, 8 times 2, 8 times 3, 8 times 4, 8 times 5, 8 times 6, 8 times 7. 8 times. And when you add it all up, this is what you get here. And just imagine, right? I meant to ask this before. This is what happened. But imagine you did throw a ball in the air, right? Any of you kick a ball or throw a ball. If you throw a ball up in the air, you know, some force, what happens to the ball after it leaves your hand? Well, it goes up and then comes back down, right? Anytime you throw something, it goes up and comes back down. Now picture a quadratic, like a parabola, right? Could a ball being thrown be modeled by a parabola? Right, up and then back down, right? Kicking a soccer ball up and then back down. Throwing a pen up in the air and then coming back down, right? So imagine those things. Yeah, well, I guess a ball going up in the air, coming back down, right? It has that, you throw it up, but then it comes back down. It's kind of like the roller coaster shape, the parabola, right? Okay. So if you pause and you want to keep going, you want to do it on your own, or you can copy this. When you graph it, this is what you get, minus these points here. So we have time, and we go, right? And here are the key features. We have the axis of symmetry split right down the middle through the maximum point, which is the vertex, right here. It's a parabola, which we're glad, that means it's quadratic. So we got our X-intercept over here, right here at 8, 0. And we also have another X-intercept here at 0, 0. But, interesting enough, we have a Y-intercept also at 0, 0. And that happens with quadratics where one of the X-intercepts could be the same as the Y-intercept, like right here. But yeah, picture that. You throw the ball up in the air. It loses its speed and then comes back down, right? Forget these ones past here. We shouldn't count these two. If you blocked out this over here. See if I could scribble it out. Yeah, forget this here. Oh, and same over here, because that doesn't represent it. Okay, and when we say from 0 to 8, we covered ourselves, because you can connect those dots, and we get the, boom, perfect. Okay, so that is part 1. Oh, then I gave you an exit ticket, right? Wait, let's see. Pause that for a second. Whoa. Let's keep that for a second. Oh yeah, okay, got it. Sorry, everybody. There is an exit ticket. You can wait to the end. Come back to it. Okay. I'd say we save it. Nah, let's do it. It's in the order. No, we'll come back to it. I like that idea. So you have the exit ticket. I'll come back to it. Okay. I'm going to pause this to end this video. Or, should we just keep going? I'm going to keep going. What the heck? We've learned how roller coasters, this is the next part of our study of quadratics. We've learned how roller coasters can relate to mathematics by focusing on the maximum height of the roller coaster, right? Let's explore what happens on another part of the roller coaster, right? So from Friday's lesson, it was up, that lift hill, and then that first drop. Okay? We are going to focus on this other part. Okay, and I do have a video, so get your hands up, get ready. We're going to focus on this part. The second drop and back up. It doesn't go very far, I think. But I'll show you that again. We're going to focus, I'll tell you when. Ready? From here and down and then right to there. All right, just that second dip where we go down and back up. Okay, so let me move on to that next slide here. Cool. So you should have if you want to pull up the handout, or you can do it in your notebook, it says Karen is studying another part of the same roller coaster ride from lesson 1. The quadratic function below can calculate the height in feet of the roller coaster after X seconds, just like before. Okay, so it's quadratic. And in this time, I want you to find the height of this roller coaster in feet for the first 12 seconds of this second part of the ride, right? And down and back up. Okay, that's not exactly make any sense in the sense that it wouldn't take 12 seconds to do that part of a ride, but I just wanted you to get a visual of what part we're studying. Okay, so good time to pause, try it yourself. I'm going to keep going with it and show you what I have for this one. So whoa, that's not what I wanted. That's terrible. That's not it. Let's see. Okay. Let me see if I can find that page. That's weird. It's not showing. Oh. Okay, I found it. All right, so if you wanted help plugging in, we just take the rule part, which is right here. We're going to put times 0 in. So we do 0 minus 6, orders of operations, right? Do it in parentheses first, or grouping symbols. You get negative 6. Then you're going to square it. You get 36 plus 1 is 37. You do the same thing. You put 1 in to this function. You do 1 minus 6. I don't know if I have it still. No. You put 1 minus 6, you get negative 5. Then you square it, and you add 1. And then do that for 2. Put 2 in. Subtract 6. Square it. Add 1. Keep going. Keep going. Keep going. Then try to graph the function. Okay? So now might be a good time to pause. Spoiler alert. Or keep watching. So if you do it right and you plug in the times 0 to 12, you can see this is the numbers you get. 37, 26, 17, 10, 5, 2, 1, 2, 5, 10, 17, 26, 37. Okay? And if you graphed it, it would look like this. Well, that's weird. Is this a quadratic function? Right? It doesn't look like our last quadratic function one. So here's where I asked you some questions if we were in class. It says, how would you describe the shape of this graph? Well, I would say the graph is definitely U-shaped. And this time it decreases, right? It goes down at first and then back up. And it appears the graph is symmetrical, right? It has that like back and forth pattern where, 5 is 2 and so isn't 7 2. And then 8 is 5 and 4 is 5. So it has that repeating pattern, right? And then I'll ask you, do you think this is a parabola? Right? What did you say? Would you say this is a parabola? I would say yes. The graph's parabola because it's still U-shaped. It's symmetrical. It increases and decreases in the exact same way. It's just like kind of flipped over, right? Instead of being a hill, it's more of a U shape, right? Okay. We can label the key features of the graph, right? So if you haven't, take a moment. I'm going to label them, right? But boom, there we go. Let me show it again. Boom. Going over each, up the top, we do have a Y-intercept. It's over here. It is parabola, so it has an axis of symmetry that goes straight through. There's your vertex, right? Your axis of symmetry goes through it. X-intercepts, well, does this U-shaped parabola, does it actually touch the x-axis in any way? Let's look. No, it doesn't. And guess what? That happens sometimes. X-intercepts do not have to, quadratic functions or in their parabolas don't have x-intercepts sometimes. They can hover above it, right? Number 4 is, would you describe the vertex as a maximum point? If not, how would you describe it? Do you think this is a maximum point? I would say no, right? It's actually a minimum point, right? And if you were watching the slide early of this lesson, which you probably were, I did mention that a vertex can be a maximum or a minimum. Okay, now, this is why we did our do now. Can you write an equation for the axis of symmetry for this graph? Right? And we did that in our do now. So it's a vertical line, right? It's going to come in the form x equals something. So we now can write an equation for this line because we know it's x equals whatever it goes through. In this case, it's x equals 6. Boom. So we actually know the axis of symmetry equation for this specific parabola. Kind of cool. What's this scaffolding button do? Let's see that. Oh, that's when I was making the table. I gotcha. Okay, we'll go through this super fast. All right. Hey, before we do that, let's go all the way. Let's go back to that do now. Go back to that exit ticket. Okay. Can you sketch a parabola that has 2 X-intercepts? Label all the key features. Can you sketch a parabola that only has 1 X-intercept? Could you picture what that looks like? And could you draw a parabola that has no X-intercepts, right? So pause me, and then maybe take a look. I can draw some, I know, if I hit the page of it, but there might be other ones you could draw, right? And if you didn't pause, there you go, right? Here is a parabola that touches the x-axis twice, and is number 1. You can see that this hill one only touches the x-axis once, right here, which actually means it only has 1 x-intercept. And then here you go, this one stayed below the x-axis, so no x-intercepts. Right? Could you draw some of the ones that were today's one that have these characteristics? Maybe, maybe not. Okay, I think that is the end of the lesson. So I'll see you guys on the other side of the lesson.